Continuation of permutations involving identical objects, and we're going to take a look at something called pathway problems as the class laughs at me. Pathway problems are a pretty specific type question, and it's along the lines of determine the number of paths So we want to determine the number of paths from A to B, and usually it's set up similarly every time, so there isn't real confusion in the setup. And it's usually only moving in one direction. If we were able to move left as well, we'd end up with infinite number of paths, so moving only right or down. And what we're going to have is we're going to have a grid, a rectangular grid with a number of paths built in. So let's draw, I don't know, let's go with a 2x4 grid. Think of it as maybe city blocks. Good times. So we have a 2x4 grid. And this falls into permutations involving identical objects somehow. So we have some sort of the solution to this, the number of pathways. Well, we could count. We could just say, okay, starting at A, I could go, oh, there's one way to get there. And then we could start counting. But the counting of the pathways isn't going to make it very easy once these things get really big. So what I want you to do is I want you to take a second. I want you to talk to your neighbors. How does this fit into permutations involving identical objects? What is the thing that's repeating? What's the thing that we have a total number of? So take a second. Talk to your little neighbors. So what happens when we take a look at this is we have 1, 2, 3, 4 moves down. So 4 repeated moves down. We have 2 moves to the right. And what exactly is the total number of objects is how many moves do we have to make in total? We have to make 6 moves in total. So 6 factorial over 4 factorial, 2 factorial. So let me just maybe write that in. That's total moves. That is down, and 2 is to the right. 6 factorial divided by 4 factorial is 6 times 5 is 30, divided by 2, I think that should be, someone roll that through your calculator, but I think that's 15. 15 total moves. Okay, so 15 total different paths from A to B. Now that's, in a 4x2 grid, that's quite a few, I would think. You know, like we have, there's 1 there, 2. Counting them is going to become a little bit confusing. This formula works very nicely for rectangular grids. As soon as we change the shape of this thing into not a rectangle with odd little nodes and stuff like that, we're going to have a little bit of problems. This pathway problem we can do a little bit differently, and I like to call it something else. It uses the second best game in The Price is Right. First best game being what, Tay? Anyone? Price is Right, yep. First best game. The Matterhorn, clearly. Second best game is Plinko. So I call these Plinko problems. What I'm going to do, I'm going to redraw that grid. I'm going to draw it on angle. You guys can just draw it normally and rotate your paper, but I don't have that ability. I'm going to draw it on angle. The reason why I have it drawn on angle is because I want right and down to be both kind of in a gravity situation, kind of downhill looking thing, because I don't want things going uphill. This is a little bit different than how I did the first example, in that I'm going to count how many lines come into specific nodes. Here's a node. From uphill, how many ways from A is there to get to that node? Well, one way, just straight there. This node here, how many nodes or how many ways are there to get there? also just one way. You can only go straight there. I'm not counting the number of moves. I'm counting the number of different ways there. One on the edge, one on the edge, one on the edge, one on the edge. This node right here, 2 ways to get there. Up and down, to the right and down. This node, 3. This node, 4. Now, how am I achieving that is I'm counting how many ways, how many paths there are into the lines that are coming into that node. So if we take a look at this 3, the only way to get to that 3 is to pass through this 1 and this 2. Those are the only 2 lines that come into that 3. So all I'm doing is adding together those 2 numbers. 1 and 2 gives me 3. Very, very quick way to fill in the nodes. 2 and 1 is 3. 3 and 3 is 6. 4 and 6 is 10. 5, 15 is our answer. So you're just adding the paths that are coming into our specific node. What I'm going to do is I'm going to draw 3 examples. And they're going to look quite a bit different. And I'm going to ask you guys to see if you can come up with the answer using this kind of Plinko method. This one's probably going to be quite big. From A to B. Usually the most annoying part is trying to redraw the picture. So we'll start throwing some random weird things in there. Assume all these lines touch. Just not a very good drawer. Let's have. Okay, there we go. A to B, A to B, A to B. Question B, C, and D. You and your neighborly neighbor, let's figure out those solutions. Now's an opportune time to figure those out. We got 1, 1, 1 on the edges. 2, 3. One of the things that you run into is that here I don't know if on this corner node, am I writing in 56 or am I writing 1? If we trace back coming into this node, there's only 1 line coming into that node, so that's just 56 ways. It's not going to be just one way to get there. It's 56 ways. So this is also 35, and this is also 35. Start to get into somewhat large numbers. $1.40, 126-ish, 182-ish. Oh, geez. 231-ish. 371. 2, 3, 4, 413. 784. That's my guess. Yep. So 28 for the C. 72 for D.